This video is going to discuss the definite integral and their relationship to Riemann left-hand sums. Okay, so previously we saw that the Riemann left-hand sum, we just have to think of it as the product, or the sum of rectangles, right? So each delta x, this was the width, and each f of x was the height, and so area of a rectangle is width times height, and so we did that over a certain number of intervals, k intervals to be precise, and added them up to get the Riemann left-hand sum. Now, to obtain a better estimate, what we actually need to do is, well, increase the number of rectangles, right? Smaller rectangles give you a better picture of the overall product, and actually what we want to do is increase it to infinity. Okay, and so what we're going to do is find n of them and then look at the limit as you increase that. But now the limit may or may not exist. I can tell you that in this case, since we're looking at areas, the limit will exist. But the question is how to do that. So mathematicians long before us determined that to compute this limit, they're just going to introduce a bit of notation called the definite integral. And it's defined to be the value of a function, or the definite integral is you compute it, you can find the antiderivative, but evaluate it at a and b. Okay, and we'll see later using the fundamental theorem of calculus how to do this algebraically. For right now, we just want to get the idea out there that, okay, over an interval, if we look at the antiderivative over that interval, that is going to be this limit. So a couple notes here. The function inside the antiderivative, or the function that we're to find the antiderivative of, must be continuous. If it is positive, okay, so think of it as a parabola that never touches the x-axis. For example, we could be here, and we have to find the area. So the antiderivative would just give us the area between the function and the x-axis. If it's sometimes positive, sometimes negative, we have to compute what I call the net area. And so what this is we compute the area above the x-axis, area below the x-axis. Area isn't negative by itself, it's a positive quantity. There's always some area. But we have to do a subtraction. We have to subtract the area below the x-axis because technically it's signed area, so it's just means that it's below the x-axis, so we're going to think of it as a negative area just due to where it is, not due to its physical quantity. Okay, and so in this example, we're going to work through that actually. So this is telling us, okay, find the area underneath the function f between 0 and 5. Okay, so what I need to do is, this is going to be the area above x-axis minus area below x-axis. Okay, and so if I do this calculation out, let's see, so this one happens to have nice geometry that I can use. So there's area here that's positive, area here that's positive, and I'm an awesome colorer. Totally staying inside the lines. Okay, so those are my two areas. And then here is the one area that is negative. Okay, so it's below the x-axis. So if I do the calculations for area above, so I'm going to say, and let's actually use proper notation, so integral from 0 to 5 of f of x dx. This is going to equal, okay, area above, the area of that is 1/2 times 1 times 1 plus, and then the area of the right part is 1/2 times 2 times 2. And then subtract off the area of the purple triangle, which is 1/2 times 2 times 1. And this results in 1/2 plus 2 minus 1, which is 3/2. Okay. In this case, the geometry was really, really nice. I encourage you to utilize geometry whenever possible. Now, this next example isn't so pretty. You can graph it in Wolfram Alpha, whatever you want. It's not going to be pretty. So what we want to do is estimate. Okay, so this is the word estimate. You should read as find a Riemann sum. Okay, estimate the value of this integral. Note that the bound, I had to change it. Otherwise, the function doesn't exist at 0. So 1 to 6. Okay, so we're going to use Riemann sums. So we're going to find rectangles, areas of rectangles, add them all up. And then after we do all that, then we're going to use Wolfram Alpha. Okay, so let's turn to Excel. Alright, so I need to make a table. And maybe I will do, no, I'm going to leave it like this. So I'm going to have a change in x value, my x values, and my y values, my heights. Okay, so x, I need to start at 1, and then I'm going to take a relatively small change in x. I'm going to do 0.1. Okay, just because the smaller the change, the more accurate your answer is going to be to the real answer. So I'm going to take 0.1 to be my change. So each x value, subsequent x value, I need to start with the one that I had above and add 0.1. Okay, and I'm just going to drag this down until I get to 6. So it's going to be a while. Oh, and I have the wrong value. I need 0.1 and then drag that down. Oh, and I went too far. Okay, so I can delete these. And also, I actually do want to delete 6 because, again, these are left endpoints. 6 is going to be a right endpoint, the right endpoint of the interval, so I don't actually want that. So I just want to go up to 5.9. Okay, so then I can compute the function value by doing, okay, so let's see, it was 2 to the power of 0.5 times my x value times natural log of 2 times my x value. Okay, compute that, and I can double click on the lower right corner to have it compute everything for me. Okay, so these are all my heights. Now for the rectangle areas, what I need to do is I need to take my height, okay, that's the height of my rectangle, times the width, and the width is my change in x, and I'm actually going to hard code that in 0.1, 0.1, just so that I don't have to worry about cell referencing here. So again, this is height, D3, times width, okay, and have Excel compute all those, and then I'm going to say value of definite integral from 1 to 6, and that value I need to sum up the rectangle areas. Okay, and so I get about 13.13. Okay, and so now I can check this compared to Wolfram Alpha, and I have it here, but we'll just pretend like we don't know that. So in Wolfram Alpha, we can do integrate is the command, and then type in the function, so 2 to the power of 0.5 x, and then times natural log of 2x, and then it requires a couple arguments. It requires comma x, comma lower bound, which is 1, comma 6, have it compute for us, And then Wolfram does its magic and tells us that the exact answer is 39.07. Okay, so moral of the story, we got an estimate that was 38.13. Wolfram Alpha said the exact answer was 39.07, something like that, I forget. But we need to be able to do it both ways, both using Riemann sums and using Wolfram Alpha, and then there will be a third way to do it algebraically, which this one we cannot do. Okay, we cannot do that one algebraically. Okay, so that's a brief glimpse at definite integrals, their definition, and their relationship to Riemann sums.